Hello everyone and welcome to lesson 11.4, Advanced Measurement. There should be no new material in this lesson whatsoever. You are instead just going to focus on perfecting the skills we've already learned by doing some practice problems. Our first section is going to look at geometric probability. Your first question has a ship is known to have sunk in the ocean in a square region 100 miles on a side. A salvage vessel anchors at a random spot in this square. The driver searches 1 mile in all directions from the point on the ocean floor directly below the vessel. What is the approximate probability that they locate the sunken ship on the first try? So basically in this problem, you're searching an area that's in the shape of a square where each side's 100, and you're going to basically stake somewhere in that square and make a circle with a radius of 1 mile and search in that area. So if I want to figure out the probability that I get it on my first try, that would be the area of the circle over the area of the square. I simply plug in and I get 0.000314, so very slim chance. All right, next question is to deal with the dartboard. We have a regulation dartboard, 18 inches across. They go ahead and give me the area of the bullseye for both a single bullseye and a double bullseye. It makes my life so much easier. Oh, guys, I have to pause. I'll be back in a second. Sorry about that. So they go ahead and they give us the area of both the bullseyes, which makes life really quite simple. We're able to simply plug in the numbers we want. Remember, we do the area that we're interested in over the whole area, and we produce both probabilities. Here we have a very similar example, except now we're dealing with physical wedges of the board, and we're assuming that those wedges go all the way to the center to make life easier. I know that the area of each section is actually going to be the same because they're all equal in length or in width. So I ended up just doing 3 times 18 degrees over 360 because 18 degrees is how many times 20 goes into 360 degrees times pi r squared, and that produced a probability of 0.15. Our next problem looks at area of the shaded region of a pentagon, and it's a little bit more complicated. To get the area of my shaded region, I have to do the area of my big pentagon and then subtract the area of the small pentagon. So my big pentagon is going to have a formula, 1/2 perimeter times apothem. Same thing with the small pentagon. Perimeter is really easy to find. I simply plug in the number of sides, which is 5, times the side length for both. I can find the degrees in each corner by doing n-2 times 180. As you can see, that produces 108, which is this corner right here. I then need half of that in order to use this triangle I've got right here. And why on earth would I call that in root 3? That should not say in root 3 right there, because that is not a 30, 60, 90 triangle. So ignore that. Okay? So that is a mistake. Don't write that down. No. Okay. So you've got 54 degrees, and that's not 2n. Yeesh. Don't do things when you're tired, folks. Okay, ignore all of that. 54 degrees is all that matters, and you need to know that the side length is 8, so half of my side is what I'm going to use in my calculations. That's an adjacent side, so if I want to find the apothem, I'm going to use tangent, because tangent equals opposite over adjacent. I use the apothem respectively in both of my different pentagons, and I get trig values for both. Then once you've got that, you simply plug it all into the formula. Remember, 1/2 perimeter of the big times the apothem minus 1/2 perimeter of the small times the apothem of the small. Plug it in, put it in your calculator, and you get the answer. Our next question has to deal with an isosceles triangle, where I have a base of 12 centimeters and base angles of 30 degrees. Drawing this is really important, so that's what I did. I drew it in. I drew in my 30-degree angle, split the triangle in half to make two 30, 60, 90 triangles, so I'm able to use my ratios really carefully. I see that the base, when I split it in half, makes 6, and that 6 is apart from my 60-degree angle, so it's my n root 3 side. When I then solve that for n, I end up getting 2 root 3, which happens in this step. That 2 root 3 is in fact the height of my triangle. I can also get the legs of my triangle by doing 2n, which would then leave me with 4 root 3. So my perimeter is all of my sides added together. 2 legs and a base, and my area is 1/2 base times height, as you can see there. The last question, or the next question in this section, is a little different. It's a regular hexagon, but we've cut it up in some strange ways. We've divided it in half and then cut straight across to make 90-degree angles there. What it does is it forms four 30, 60, 90 triangles, 1, 2, 3, 4, and 2 rectangles, these 2 here. They are not squares. So my 30, 60, 90 triangle, that has to be 60 degrees because the big angle is 120, which again we could find using n minus 2 times 180 over n if we needed to. This is 60, so across from it's my n root 3 side. Across my 90-degree angle is 2n. Well, I know my side length is 6, so n must be 3. This little piece right here is 3. So my shaded my triangle is 1/2 base times height. The base of my triangle must be n root 3, so that's 3 root 3. And my height of my triangle must simply be n, which is 3. Now this rectangle here is equal to length times width. Well, my length is clearly 6, and my width is this n root 3. So 6, and then I get 3 root 3. We simply now plug all of this in. Area of my shaded region equals area of the triangle, which is right here, plus area of the rectangle, which is here. I reduced it, got my exact answer, which is 45 over 2 square root 3, and my approximated answer, which is 38.9711. Now, if I want to get the probability that a point chosen at random lies in the shaded region, I have to do the probability of the shaded over the whole. Well, I can't do that until I have the area of the whole. So, area of the whole, 1/2 perimeter times apothem, I need the apothem. That's what this orange triangle over here is showing. If I were to draw to the center of my hexagon and extend 2 radii out, I know that this little piece right here has to be 3 because it's half of a side length. I know this is a 60-degree angle, so I know this has to be an n root 3 side where this is an n side, so this is 3 root 3. So my apothem ends up being 3 root 3. My perimeter, I have 6 sides, each of length 6, so that's pretty easy. Times the apothem, we get 54 square root 3. I then simply plug in my numbers. I can get a reduced fraction, and I can also get a decimal. Makes quite a nice problem. Okay, next we've got 2 composite area problems. Easiest way to deal with these is break them up into shapes. As you can see here, this funky looking thing breaks up into 3 beautiful rectangles. I've shown you how I've divided mine. This one over here, we have to use a little bit of special right triangles to get some of the things we need. Remember, your base and your height have to be perpendicular on a triangle. So if I establish that this is the base, my height has to go from the base to the vertex and hit at a 90-degree angle. So we had to use special right triangles to find the height. So we know that anything with a single tick mark is 10. I was able to label lots of extra sides because of that. I know that my height has to be that n root 3, 5 root 3, and my base has to be 2 times n. Well, n is here, so 2n would be both of these, and end up being 10. With that rectangle, we've length times width, both are 10, super easy. Plug it in, my area equals 2 of those triangles plus a rectangle, and I get a really beautiful answer at the end. Well, I really don't, but we get an answer. So, now let's talk similarity. Similarity, not bad. Y'all are awesome at similarity. I've been really impressed so far. They begin by telling me that I have 2 similar cylinders with heights of 3 and 7. That means that my scale factor A over B has to be 3 over 7. They then tell me that the area of the base of the smaller cylinder is 18 centimeters squared, and I want to find the area of the base of the larger one. So if we're talking about area, then we need to do A squared over B squared, which I calculated first right here, 3 squared over 7 squared. Then I set up a proportion. That 9 over 49 equals, well, notice I've got the smaller of the 2 numbers on top, and they give me the smaller cylinder's base area. So that's going to plug in on top of my proportion. Plug it in, cross multiply, divide, and you get your answer. Okay, next question. We've got two similar rectangular prisms with volumes, respectively. The key to this, plug in your numbers, a cubed over b cubed equals 16 over 54. You have to reduce that first. Once I reduce it, it's really easy to see that that becomes 8 over 27. And 8 over 27 is really useful because they're both perfect cubes. 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. So I get that a is 2 and b is 3. So now I can use 2 over 3 as my scale factor to find the missing height. So I have 2 over 3 equals 4 over x, cross multiply and solve. How many cubic inches are in a cubic foot? Oh, I love these problems. So I know that if we're just looking at a length, there is 1 inch in a foot. So the scale factor is 1 to 12. So if we take that to cubic, that means we have to cube everything involved. So we get a cubed over b cubed equals 1 cube over 12 cubed, or 1 over 1,728. So there are 1,728 inches cubed in 1 cubic foot, which is pretty cool. And then we have a problem where we've got two similar pyramids with lateral areas given. Well, that's area, so I'm going to have to use a squared over b squared. Plug in, I can reduce. I end up with a equals 1 and b equals 3. I plug in then to volume, a cubed over b cubed, that's 1 cubed over 3 cubed equals 10 over x, because they give me the smaller piece. I end up getting x equals 27 times 10, or 270 meters cubed. And last but not least, we have a conical paper cup that is 3 inches high and holds 4 ounces of water. We're going to then change the water level so that now it only contains 2 ounces. Now, we're now talking about volume. If we're talking about ounces, we're talking about volume. So we need to use a cubed over b cubed equals 2 over 4, reduce it to 1 over 2. So a equals 1 and b equals the cube root of 2. Do not panic. I know you'll have not heard of a cube root before, but that's okay. Your calculator knows what it is. You don't have to. You will learn that next year in Algebra 2, I promise. So I'm now going to plug in my a and b, where I have a over b, 1 over the cube root of 2 equals h over 3. Cross multiply, the cube root of 2 times h equals 3. Divide, and this is where your calculator comes in. You have a beautiful button right here on your calculator. If you hit Control and then the caret button, it's going to give you n root x. You can then tell it to do the cube root of 2. Super lovely. Use it. Spits out this lovely answer, and you get what the height should be. Thank you all so much. Be patient. I'm sure you're going to get this. It's not that bad. I know this was fast. You might want to go back, rewatch it, pause, whatever you need to do. Come in and see us if you need any help. Thank you all so much and have a great day. Thank you.